And here we are, back once again. So, not many people attending this morning, which is kind of sad. Well, some of our regulars are here, and I'm really glad to see you guys over here. We're getting a few participants. One of you guys is even doubled here. uh, yeah. So, just a very quick recap of last week. So we talked about sample distributions and estimation, and some of the exercises and the questions had to do with that. There was a lot of things that we had to recap, and a lot of theory that we had to cover in order to get to where we got. And like I said before, there was a person asking in previous lectures, how much of this do we need to understand? Well, the thing is, need to is a strong word. I think you should aim to understand as much of it as possible. But given that that's not the option for everyone to understand how the mathematics works there, just try to get the idea that much of this is based on a couple of things. So when you average over a large number of samples, or you sample taking a large number of points of your random variable, then averaging out pushes down the variance. So the average converges towards the expected value. That's one important thing. And the average of a sample is in itself a random variable. I mean, think about it. If you take just one sample, then that's just your random variable. If you take several samples, then it has the same expected value, but smaller variance, so it pushes it to a narrower situation, a narrower distribution. So, and the average of a large number a large sample tends to have a normal distribution roughly. And the central limit theorem was, that was the main part of the central limit theorem. So a normalized or standardized sample mean tends to be close to the 0-1 normal distribution. So this part here, this mu here, fixes it at the 0, the expected value at 0, and then dividing by the standard deviation divided by the square root of n fixes the fact that as n grows larger, then the variance goes down. So this fixes that. So we get to something that is close to N01 normal distribution. And we use this pretty liberally, meaning that we very often assume that things to be normally distributed when dealing with averages. And then we have the sample variance, and we talked about that a lot. The main part here, then, we aim for using that in terms of deriving what we call the confidence intervals. So the confidence intervals role was very important. Not going to go into the mathematics here. This is just a recap of previous one. Of course, spent many minutes on this. But if you think about it, then we had a random variable, which is really the interval is random. So when you take different samples, the interval moves. And the idea here is that if you have a certain parameter, that the confidence intervals certainty level, or the when you say 95% certainty level or confidence level, it means that 95% of the time your random variable will get values such that the actual parameter is contained in that interval. So the alpha is the probability of error in the sense that it's the probability that you get values such that the actual parameter is outside that range. We'll be using this idea today. So we talked about the risk level. So alpha is the risk of getting a value that getting a interval that does not contain your actual value, even if everything you assumed is correct. If what you assume is not correct, then all bets are off. That's the thing you have to understand. These are all based on the idea that you assume a certain kind of distribution, and then you take a sample, and then you have a random variable that has this property that if everything you assumed about the distribution has these properties, then the probability is alpha that your actual parameter is not inside that region, the confidence interval. And we had the confidence intervals, we derived them under the assumption that things are normally distributed. The same thing, under the assumption that things are normally distributed, we came up with these limits for the variance as well. We talked about the t distribution, which is kind of like a wider range, because here we had to make use of this sample deviation instead of the known variance or known standard deviation, and we had this t distribution, which has it's wider. It's like a normal. It's a bit like the normal distribution. When n grows towards infinity, it approaches the 0-1 normal distribution, but it's wider, and we use this to correct for the fact that we don't know the variance. Our estimate of the variance is a random variable, and that's why it has a bigger uncertainty there. So these two tests, whether to use the t or the z, that's up to the idea that do you know the variance, or can you rely that the variance is known, or do you have to resort to the sample variance? So here we have S, and in this other one we had the sigma. Then we derived the confidence interval for the variance. We was it the estimate of the variance when fixed with this actual variance. This is a chi-squared distributed. So this is like the proportion of how much of this sample variance is from the actual variance. And it's chi-squared distributed, meaning that with n being the greater, the larger the n, the greater this variance. This can be thought of as the sum of squares of normally distributed variables, because there's a normally distributed variables. These are roughly normally distributed. The deviations, this x bar minus xi, and it's a sum of those. Not going to go into detail, but then we derive the confidence interval here. So the actual variance is between these two numbers with probability 1 minus alpha. And we have this this way of calculating it. And we have to look it up from the chi-squared distribution in here. And then we had the relative proportion, where we had a nicer thing when we have a binomial distribution. Then it's just, this can be thought of just as an application of the one with the, it's not, the variance is not known, but we use here z instead of t because of the fact that the binomial distribution is so closely mimicked by the normal distribution. So this was like when you have a binomial distribution, then you can use this. All right. So what we are going to do today, and also I was going to say tomorrow, but tomorrow we don't have lectures. We have lectures on Wednesday of next week. What we're going to do on these two lectures is this is the last topic, we're going to talk about statistical testing. So the idea is that we have a hypothesis. So I hope that you know enough of the terminology in science and research and that sort of stuff, that you know what a hypothesis means. So a hypothesis is a postulate, or a statement, a proposition about the property of a distribution, in this case, that is either true or false. Hypothesis may be wrong. It may be inaccurate as well. I mean, we may state something like, this rod is 1 meter long, and then we measure it and it's 99.81 centimeters. So is that false or true, or is it just a little bit inaccurate? That's a matter of debate. But let's just say that we are focusing on statements that are either true or false. So most of the time, this is a statement about a parameter such as expected value or variance. And we're actually focusing on statements about expected values here. Also focusing on statements about variance a little bit, but not much more. So statements such as, you know, the expected value is pretty close to zero, or the statement that the two expected values, I mean, we have two variables and their expected values are the same, or something like this. So a test of a hypothesis is you can think of it as an experiment, and you should think of it as an experiment that is done before the fact. So, you know, ex ante, before you have your data, you should formulate your hypothesis. Of course, that's not how it works. You usually have your data, you look at it and you formulate a hypothesis, but that's usually the dirty way. I mean, from the point of view of just philosophy of science, what you should do is you should formulate your hypothesis, then design your experiment that tests your hypothesis, and then carry out the experiment and look at the result. Does it actually support your hypothesis? So this is what we do. This is really deep stuff, in the sense that this applies not just to statistics. It should apply to everything else that you do when you try to figure out how things are. Is something true or false, and so forth. So this is a very deep issue about the philosophy of science, but we are just framing it or pushing it into this narrow frame of normally distributed random variables to test whether they are, whether there is a certain degree of confidence, if you will. We talked about the confidence intervals, and those formulas will be played out here as well. So what we will do is we will formulate a test of the statement that you make, and you take a sample of the distribution and come up with a probability that is interpreted as the likelihood of this hypothesis being true or false. And when I say it's interpreted as the likelihood of the hypothesis being true or false, really what we are doing is that, is this sample really improbable if our conservative hypothesis is true? And by conservative hypothesis, we mean that we usually make two competing hypotheses. The null hypothesis, which is a statement that doesn't really say much about anything, or that is a conservative assumption about the nature of things. And then we have things. And then we have the alternative hypothesis, which is the one that you really are testing for, or whether you will accept it or not. And you're being conservative in the sense that you need strong evidence to support your alternative hypothesis, or in fact, not really support your alternative hypothesis, instead to reject the null hypothesis. And then the alternative hypothesis is accepted, not because you have direct evidence for it, but because you have established that the results you got were very unlikely if your null hypothesis was true. And really, there's a thing that needs to be addressed here in several ways to understand how it is. Oh, let me see, 882, is that 882? Yeah. So I'm going to show you shortly a web comic that discusses this, but not just yet. We talked about this later. So what we do to testing is, again, so we postulate the null hypothesis and alternative hypothesis, and the test is carried out with the assumption that the null hypothesis is true. You have to understand that then everything you have here is predicated on the idea that if the null hypothesis is true, then something. And when you get a result that is very unlikely, then you reject the null hypothesis. if you get a result that is, you know, your garden variety result, a result that could be just as well produced by the null hypothesis, then you do not reject it. So this is really a deep matter in the sense that we could do this in very different ways. We could do this in different ways that are radically different from this. This seems to be, to many people, this seems an overtly conservative way, and the critique is in play. I mean, the critique is warranted, but not going to, I don't have enough time to discuss the philosophical matter here in too much detail, but you have to understand that it's not irrelevant here. All right. If the result indicates strongly that the null hypothesis is false, or you know, not strongly, you know, and we'll talk about this. If the null hypothesis is not rejected, then what the test result gives you is really, it doesn't give you much anything. It's just that, okay, things are still normal, right? The hypothesis test itself is random. There are two things. It's a random variable, so it's susceptible to interpretation error, not just interpretation error in the sense that, okay, we look at the result and we interpret it in one way, but just the fundamental interpretation error in the sense that if you look at the result beforehand, you have to decide when are you going to interpret this as a certain kind of test result. And when you introduce this idea that, okay, this is how I will interpret it, you will introduce the possibility of making a mistake or error. So there are two kinds of ways in which case the test may produce a wrong result. So we call the type 1 error, which is called a false positive. So this means that your null hypothesis is rejected and the alternative hypothesis is accepted, even though your null hypothesis is true. So this is the sort of error that we can control. We can control this error because we know all the assumptions related to the null hypothesis. So the null hypothesis must always be framed in such a way, for instance, that you know the distribution, or you know, you postulate the distribution that you know of, and then under that assumption that the distribution is like this, then you carry out the test and look at the result. So the false positive means that you did everything like this. You came up with a very, very uncommon result. You deduce that the null hypothesis is wrong, but really it was just a fluke, just a random occurrence, because, you know, very rare events happen sometimes. So this probability can be controlled, and that will be the alpha. I mean, it's really mathematically speaking, it's the same alpha as we had in the confidence intervals. Then there's another type of error, the false negative. It means that you accept the null hypothesis, even though the null hypothesis is false. And usually this cannot be controlled. It cannot be controlled because the only way you can assess probabilities is by making assumptions about how things are. The null hypothesis captures all your relevant assumptions, but if your assumptions are wrong, then you don't know anything about it. That's really the important thing to understand here. This type 2 error cannot be controlled. You cannot mathematically control it. If you recall in our examples, or was it in the exercises? Yeah, in the exercises, we had this question about the two schools, or you know, the school A, and we had a certain average or certain average result, and we had a certain expected value, and then we were asked, what do you think is the probability that this school A students get this result or worse, and do you think that these students that in your sample are in fact from school A? Now here comes these two types of errors. So we can make an error by saying that, okay, we say these are not from school A, but they are. And that's the probability that we got. We got that about 1.6% chance that they could be this bad, the students could be this bad if they are from that school. So we got about 1.6% chance that we did a false positive, meaning that we rejected the idea that they are from school A, even though they were. That we know, that would be the alpha. On the other hand, we cannot assess the probability of a false negative, meaning that, okay, we accept this result even though it's false, because we cannot know what the alternative hypothesis entails in total. I mean, we don't know anything about the other schools. So that's the thing here to understand. So the risk level is often predetermined, but this is by no means necessary. We can just calculate these things and then decide on the risk level later. Usually, those people who think we need to be hygienic about this think that we have to set the risk level beforehand and then just either accept or reject. But that's not actually how it's usually done. In fact, what is usually done is we calculate what is called a p-value. I'll show it shortly what that means. And then we just mark it as either, 1 star, 2 star, or 3 star p-values. This is often the case if you use software like R, which has the statistics, it's a statistics software, and you can calculate things like linear regression. Sadly, the topic that is not part of this course, one that I think is highly important in statistical analysis, much overlooked, but never mind that. We get certain coefficients and we get their p-values, and they would come out at alpha, at p-values that are smaller than or equal to either the 0.05, 0.01, or 0.001. And then these would be marked as at 1 star, 2 star, 3 star. And if it has no stars, then we consider that to be a case where the null hypothesis remains in place. I'll show that shortly. The type 2 error, we often denote it by beta. We cannot often calculate as such. And the null hypothesis is what we call the ground assumption of the model. If the model is correct, then we can say something about how probably it produces the anomalous result. But if it's wrong, we don't actually know how it is wrong. We just postulate that it's wrong, and that's it. So there are two things that we can say for sure. We can say that if the sample size is fixed, then increasing one or decreasing one of these types of errors will increase the other type of error. So if you want to make sure you have no possibility of false positives, then you cannot say anything about how probable false negatives are, and vice versa. If you increase the sample size, both types of error probabilities do go down. Well, it doesn't mean that they go down towards zero. It's not going to increase your error, right? And alpha, especially the alpha levels, because of the nature of these assumptions, then by increasing the sample size, your probability alpha, that type 1 error probability goes down. In this material, we assume that the hypothesis is about a parameter of the distribution, such as expected value. And usually the possible null hypothesis that we make is that this parameter is some theta 0. So this theta could be either the expected value or the variance or something else. And the parameter has a certain predetermined value. It could be, it could be the correlation between two variables. It could be the something like, the hypothesis could also be a statement like, the two variables have the same variance, or two variables have the same expected value, and so forth. It could be like this, but very often we then frame it as a computational variable that then has a certain distribution, and then it's about the distribution of that particular variable that we mentioned. We then test for. Given that this is a null hypothesis, alternative hypothesis can be such that, okay, it's greater than this, or it's smaller than this, or I see, sometimes that is just different, not the same. Given a risk level alpha, we test the hypothesis by finding the confidence interval, either the confidence interval or just the upper or lower bound of the confidence interval. One or the other, or both. So if we're looking for the null hypothesis, for example, that the expected value is not equal to 0. Well, the null hypothesis is that the expected value is 0. So what we will do is we will count, if our alpha is 0.05, what we will do is we'll calculate the 95% confidence interval for the expected value. And if 0 is not on that interval, then we reject the null hypothesis. This is how we will do it. On the other hand, if our alternative hypothesis is that the expected value is greater than 0, then we just look for alpha level on the up end of the interval at 0.05, and then if we reject the hypothesis there, so if our estimate, in this case the confidence interval, the upper region of the confidence interval the lower region of the confidence interval is above 0, it means that the confidence interval, wherever it may be, it will always contain only positive values. Then we reject the hypothesis that it's 0 and accept the hypothesis that it's greater than 0, for example. In order to carry out the test, whatever that may be, then we have to come up with what is called the test statistics. That's a variable that is a random variable that depends on your sample. And if we know the distribution, remember that we have the null hypothesis. The null hypothesis postulates the distribution as well. So that gives us the possibility to calculate this probability. The problem is, of course, that if the null hypothesis is wrong, we may not even know what the distribution is. But, you know, that's why the null hypothesis is often very conservative. So what really is that we calculate what is the critical region. And the critical region then depends on what our alternative hypothesis is. And let's see, we'll mention these critical regions. Technically, we could pick any critical region, but here comes the philosophical part. We have to derive this critical region from without the use of direct math. This is part of the deciding on the critical region is part of the operationalization of this model. I talked about operationalization. It means that you connect the variables and your whatever it is that you are going to be measuring, you connect them with aspects of the real world, and you explain how these are interpreted in your model, and that's how you use the model. So operationalization is a very important part of any mathematical modeling that is then applied to the real world, because it tells you what those variables mean. And deciding on the critical region is part of the operationalization, because the critical region has to be such that it is reasonable and to assume that that's where the null hypothesis is at risk. So for instance, if the null hypothesis is that for instance, that the expected value or the variance or whatever the parameter has a certain predetermined value, and the alternative hypothesis is that in fact it is bigger than this, we choose as our critical region the tail of the distribution that contains the larger values. So if we get this critical region, is that if we get a very large value whose probability is less than or equal to alpha, under the assumption that H0 is true, then we reject the null hypothesis. So a very rare event on the part of the distribution which would occur if it were actually bigger. Well, if the hypothesis is that if the alternative hypothesis that it's different, we just choose half of the region. So here's our example. I mean, here's a one-tail test. If our alternative hypothesis is that the parameter is small, and now look, this is the distribution of the parameter. Remember that we had, this could be the, let me just give an example. For expected values, right? We're probably using the sample mean as our test statistics, or we normalize the sample mean. So this would be the normalized sample mean, and we are looking for values that are here in this region, and this would be where it's 0. Or if this would be the variance, then this would be a chi-squared distribution. Normalized sample variance would be very small here. This doesn't look like the chi-squared distribution because this looks more like a normal distribution, but it applies to any distribution here. So this would be the one where there's small values. If we get one of these values, then we reject it and we conclude that the alternative hypothesis that the value is in fact smaller than the postulated value. Here, if we don't know whether it's bigger or smaller, we just come up with a critical region, which is here higher, lower parts. This contains half the probability, this contains the other half the probability. And if we start with this null hypothesis, if we get a very large or very small value, then we're going to reject the null hypothesis and accept that it's different. These would be predetermined usually. I mean, if you see that you measure, remember that one example with the people measured at a certain country, and they have you're measuring the how tall men are in a certain country and so forth. So let's say that you were come up with a certain null hypothesis. So if you know the average that you got, and you know that the average is already smaller than your pre-postulated value. I think that was, in that example, the average came out at 178 point something in centimeters. And let's say your null hypothesis was, for some reason, was that it's 180. So you already know that it's going to be smaller, so most people will be using this small value low tail test. This is a matter of taste a little bit, but also, you know, a question of how do you formulate it before you look at the data at all, or you just look at the data and then formulate it. The latter part is not, strictly speaking, you know, pure science, but who's to say that it's wrong? I mean, that's how humans think, isn't it? I'm not going to say what is wrong and what is right, but usually try to determine it beforehand. Okay, the test statistics is then calculated, its values compared to the critical region. If it falls in the critical region, then we reject the null hypothesis and accept the alternative hypothesis. If the test statistics does not fall in the critical region, so we get one of these results here. So if we get a result that is like here, not quite in the critical region, but pretty small, then we usually, what we say that is that, okay, we got a difference, but it was not statistically significant. Statistically significant result means usually that you reject some form of null hypothesis. So if you see this language used, something is statistically significant or not, the statistical significance is predicated on all those kind of sample sizes and all that, and some predetermined alpha. Usually, when you see this without mention of any p-values, then this alpha that they use is 0.05. That's 1 in 20. I'll shortly show you some critique of this, but not quite yet. So it means that it's too common to merit rejecting the null hypothesis. So if it's a 1 in 10 shot to get some result, then you might think that, okay, let's do more experiments. Usually that's how they frame it. If you see a paper written about the effect of some medication or some other thing like this, and say that, okay, it's not, the results were not statistically significant. There was a difference, but it wasn't statistical significant. Then they would say that more research is merited. Yeah, that depends on how it goes. The result of the test may also be given by indicating the p-value. The p-value is then, just giving how far along the curve it is. So it's the alpha level, smallest alpha that would still result in rejecting the null hypothesis. So if p-value is 1 in 1 million, then you're thinking it's pretty small p-value. But really the p-value then it just indicates that there is a difference. The difference can be even very small. So understand the difference between there being a difference and the difference being statistically significant, or the difference itself being significant. So you may find, for example, let me just say, give an example. You may find that certain medication helps in some illness statistically significantly. And let's say that this is, well, I'll give a concrete example. I don't know the exact numbers, but I read this paper once that, there's the sleeping aid, which is the human hormone melatonin. So you can take it at night and it shortens the time between going to bed and falling asleep. And it's statistically significant, and the p-values are just virtually zero in all studies. So it's definitely statistically significantly reduces the time it takes to fall asleep. So you take people who don't take it or take placebo, and people who take it and measure the time it takes for them to fall asleep after they go to bed. And if you take melatonin, then that time is shorter. The expected value of the you look at the difference, and the difference is greater than zero, and it's very significant. The p-value is very small, but the difference is not big. So an average person might take, and these are just from the top of my head, that's probably not correct numbers, but let's say that the average person takes 28 minutes to fall asleep, or 32 minutes to fall asleep after they go to bed. And the person taking melatonin will take 27 minutes to fall asleep, or 29 minutes to fall asleep. So it's like a 5 to 3 minutes difference. It's statistically significant. Is it clinically significant? That's up to other people to decide. So understand that the small p-value doesn't mean that the difference is big. It just means that the probability of getting a difference this big is very small if they are the same. That's the interpretation of the p-value. So the testing produces as follows. So formulate the null hypothesis and pick an alternative hypothesis. So ideally you do this before you know anything about the outcome of the data. Assume that the null hypothesis holds and come up with the relevant distribution. So we postulate the null hypothesis, for instance, that this variable has expected value 0. We come up with a relevant distribution. Okay, so it's 0, and let's say that it's normally distributed. Choose a significance level. This is arbitrary. Usually it's 0.05, 0.01, or 0.001. Pick one or just wing it. This can be omitted as well. Just calculate the p-values. That's possible as well. Choose the test statistics. That means that you come up with a way of testing your null hypothesis. So you calculate and derive its distribution under the assumption that the null hypothesis holds. Calculate the value of t from a sample. So in this situation, you have to come up with the sample and calculate the value. Determine the p-value, or the critical region, the value where the values that you should get that would merit rejecting the null hypothesis. If you get a critical region or your p-value is smaller than alpha, reject the null hypothesis and adopt the alternative hypothesis. And if it's not, then H0, your null hypothesis, remains in place. So this is statistical testing for you. And now, you know, this is the general template for it. And I'll show you some examples of this, and we'll learn to do a couple of statistical tests here. Right. So firstly, testing the expected value, and we take the first cases where we know the variance. So this is not, it's not unlike, and it's, in fact, it's quite the same as calculating the confidence intervals. So, oh, there's a typo there. I'll have to fix that. So there's a couple of typos. Sorry about that. I don't know what's happened to that. So let's say that we have a sample of a normally distributed variable where we know the variance. We don't know necessarily the expected value. And let's say that the null hypothesis is that this expected value is some mu0. And now I'm going to just have to fix that because that's just terrible. If you have any questions regarding the material this far, then sorry about these typos. I seem to be making a lot of them these days, but no, but that, yeah, I'm gonna have to do this another way. I'm going to just a second. All right, and now I'm going to share that. Sorry for this. Okay, now that's better. So we determined the null hypothesis that the we have some predetermined value. So whatever the actual, remember that mu0 here is the one that's postulated in the null hypothesis. The actual value is mu. We will assume that it's mu0. And if we assume that it's mu0, then we can have the we have the normalized standardized, sorry, the standardized mean will have a 0, 1 normal distribution if this is mu0. If the actual expected value is mu0, then this will be 0, 1 normally distributed. If it's different from this, then this distribution will be something else. So there are two assumptions at play. One, that X is normally distributed. Well, even if X is not quite normally distributed, if the sample that we're dealing with is large, then it might be reasonable to assume that this is still roughly normally distributed. The other assumption being that this mu is mu0, and if that's true, then subtracting this from the sample mean means that this is a 0, 1 normally distributed. If it's not mu0, then its distribution still, while still normal, will have a different expected value. So now this is going to be our test statistics. This is the variable that we will test for, because we've normalized the outcome of the sample into this variable. So we come up with a critical region. So if you have a two-tail hypothesis, we choose this Z alpha such that, you know, this this holds. I'm just going to show you a picture. So what we're going to do is we're going to postulate this from the 0, 1, and we're going to have here alpha over 2 and here alpha over 2 probabilities, right? So the total probability of this region and this region will be alpha. And we're going to calculate this test statistics, Z. And if the Z falls here or here, we will conclude that the null hypothesis is false. Because with probability alpha, which is very small, we get values like this. So the probability of getting these results is very small. Here's the table, I mean, how we do it. If our null here's the null hypothesis being that mu is mu0, but the alternative hypothesis can be one of three things in this situation. Either it's smaller than what we postulated, in which case our critical region will just contain, again, it will just contain these, and the size of this will be alpha. If it's if our alternative hypothesis is that we're actually dealing with values far bigger than mu0, then our critical region will simply be these large values. And how we calculate the p-value is we calculate the value of our test statistics and we look at its value there. In this case, it's 1 minus z because, well, obviously we get this a large number here, then it gives you this part of the probability, right? Not that. So it's 1 minus that, because if you calculate the cumulative distribution function here, you get this probability. So 1 minus that is the part on the right-hand side of it. On the other hand, if it's simply that they are different, then the critical region is either of these, both of these. If it's in one of these regions, then we conclude it's different, and we choose whichever these is smaller. So I mean, if it fell here, then it's 1 minus z. If it fell here, it's a z that we are using here. So that z, like, look, this z alpha here, that's the limit. So that's, I'll draw the picture. So that's, let's take the two-tailed case. So these are the z alpha over 2, and sorry, these are my two z alphas, right? And the z, on the other hand, let's say that we get a very large value, then that's the sample average minus mu0 over. So that would be your z, in the p-value. That determines your p-value, that z. So the z alpha is the predetermined level that based, or z alpha over 2 is the one that is based on the idea that you're calculating the limits of your critical region. But this z here is the actual value you get by punching in your sample numbers into this formula, right? Because that's the test statistic, right? So the z alpha is the limit of this region, and the z is the calculated test statistics, the actual value you get for your random variable. Understand? So p-value is a random variable. This is a fixed, the critical region is a fixed region that you calculate based on the null hypothesis. Whereas the p-value is a random value that you get once you calculate the actual z from the sample. And the z is calculated by, in this case, by this formula here. Does that answer your question? Yeah, good. So there are two Z's here. The predetermined value, let me just recap one more. I just said this and I'll say it more. The predetermined values of these regions limits, those are the Z value, Z alpha or Z alpha over 2, depending on if it's 1 or 2 tail test. And then the Z, that's your random value that you get by taking the sample and then calculating it. And that the P value, in this case, the P value, if we get this 1 minus Z, then if your Z, if your Z is here, right, it turned out to be this value, then 1 minus this phi Z, it's in fact this, because the cumulative distribution, the phi gives you this probability, then 1 minus phi gives this. And why this is the minimum of the two is that if you get a very large value, you use this because then this is small. And if it's a very small value, use this because this is then small, right? So this is the case when you have a small value, and this is the case when you have a large value. Okay, here's an example. Annual rainfall in a given region is given, and we deduce this from a 100-year averages. So let's assume that over the last 100 years, this has been the rainfall. Last 5 years, so on the other hand, the average rainfall has been 89.3 millimeters. Justify your choice of alpha, your significance level, and the test whether it's reasonable to conclude that the rainfall has diminished. I didn't write this, the actual example solution here, because I will do that next week's Friday. I'll gather all these examples and we'll go through them in detail. How you go about doing this, however, is that you first determine here your test statistics. So let's think about the test statistics here. We are given this, so what we do is we define this. Our null hypothesis now would be that this mu is in fact 106. So just our null hypothesis is that mu is 106. So this is our null hypothesis now formulated. Good. That's our null hypothesis. It has asked, is it reasonable to conclude that the rainfall has diminished? So our alternative hypothesis is that mu zero, sorry, that mu is smaller than mu zero. So our alternative hypothesis here is that, that mu is smaller than mu zero, okay? So what we're going to do now is we're going to, let's go back up here. Oh, I was going down, not up. We formulated so choose a significance level. What would you choose as a significance level? Well, one thing here that might merit something is that we have 5 years of data now, and we used to have 100 years of data. So that's about 5% of the whole data. So this is not a reasonable justification, but let's say that that's 1 in 20 of the 5-year averages. So 5 years average rainfall is 89.3 millimeters on average. So that's small, okay? So that's your 5 years. Our N is 5. So let's choose alpha to be 0.05. That's 1 in 20. Our N is 5, not a very big N, right? That's last 5 years average rainfall. Test whether it's reasonable to conclude that the rainfall has diminished. So now we want to devise the Z alpha. So our Z alpha is Z, given that we've chosen alpha, I mean, here are my numbers here. I'm just drawing them here. My alpha is 0.05, so I'm going to look for Z 0.05, the Z 0.05, and that's this critical region here. Well, let's use MATLAB. So I'm going to just, okay, I'm going to calculate that, and I'm going to calculate the 0.05. So I get minus 16449. So 16449. That's now, and just looking at this picture, this minus Z alpha is now minus 16449. This here, 0, this coordinate here is minus 16449. All right. So we're going to be calculating I'm just going to share this. We're going to be calculating the Z statistics here, and that would be the average. That would be 89.3 minus 106 divided by, remember that we had here 15.3 is the sigma, because the sigma squared is the 15.3. So divided by 15.3 over the square root of 5. That's my Z now. Over here, that's my Z. So I'm going to calculate this Z. I'm not going to switch to the MATLAB view here. I'm just going to do it, so you can do it by hand if you will. 81.3 minus 106 divided by 15.3 divided by the square root of 5. And what I get is minus 3.6099. So that would be minus 3.6099. That's my result now. Now, what do you think? If I get this result here, I calculated the Z, that was minus 16449, and I got Z at minus 3.6099. What does the test say? Does it fall into the critical region? What do you think? Well, my minus Z alpha, or Z, well, this one was minus 1.65 roughly, or 45. And this Z here was about minus 3.6. So it's definitely in the critical region. So we conclude that it's reasonable to conclude that the rainfall had diminished, at least with the 0.05. But let's calculate the p-value. In order to calculate the p-value, we calculate the cumulative distribution function at that 3.6099. So norm CDF minus 3.6099. And we get about 1.5 times 10 to the minus 4. So that's 1.5 in 10,000. So it's very, very unlikely that the 5-year average is this low unless the rainfall has actually diminished significantly. There's something going, I mean, how do you interpret this? There's something going on. Yes, the rainfall is the rainfall. Yes, it's true. The rainfall that's determined by this is a random number. Yes, weather is random. But 5-year average being this low means that something is different now from the previous 100 years. And now I'm going to say an ugly word. There are people out there, and I know not everyone who hears this wants to hear this, but I don't care. So there's a climate change going on out there. And it has been established in various regions that this rainfalls, temperatures, and what have you have changed. So this 106.0 and 89.3 averages difference. It's not huge here, but the probability that it's insignificant, that it's not a real difference, but just a statistical fluke, is 1 in 10,000. And if you claim that there is no difference here and that there's no reason to believe that this is other than just random fluctuations, then you are an asshole. I'm sorry to say this. Don't go making these claims about randomness unless you understand. You know, the proper p-value here in this case, I mean, I'm just saying the real life data out there is similar, not unlike this. And if you go about claiming things like, you know, it's randomness, there's no evidence of any sort. You don't know what the hell you are talking about. And I want you guys to understand this. Now you can be literate about these differences and look at this, and you can make up your own mind. But if you don't understand how this thing goes, how this statistical testing and how these probabilities go, then don't make a fool of yourself and claim that you know how statistical significance works. All right, enough of rants here. Let's move along. I'll go through the actual mathematics later. It's not written here, but I'll go through the mathematics later with the formulas and all that. Please notice that the central limit theorem implies that for large samples, the sample mean or the sample average is approximately normally distributed, even when X is not. This means that the method can be used for variables that are not normally distributed. But I want to say this, it can be used, yes. But if the underlying variable is not normally distributed, then you have to be really careful that whatever assumptions you make about this variances and expected values and what have you, those need to be fixed and corrected for the fact that you're not dealing with normally distributed variables unless your n is huge. All right, so understand that. Okay, so that was the test when we knew the variance, and it was our simple test. But when the variance is not known, and this usually is not the case that we know we just have sample variances, and the normalized mean has the, thank you. Someone sent a link there, English, for the precipitation example. Yeah. Annual mean temperatures and precipitations. Yeah, that's nice. You can check these temperatures and those for between 2010 and that's good. That's good. Yeah. Thank you. All right, but let's move. That's good auxiliary information. And look, in my rant, what I said about the climate and all that, the truth of the matter may be whatever it is. I'm not making claims about that. I'm just saying, when you invoke an argument about random fluctuations, do please make sure that you understand what you are talking about. So if someone says that there is a statistical significance, you can't go about claiming that it's just the variance that we had before, because it's not, right? That's the point. So if you have a 100-year average and then you have a 10-year average, and the 10-year average, the latest 10-year average is way higher or way lower than the 100-year average, then something is going on. Something is different. And claiming that it's not different, that it's just random fluctuations, that's not a good argument. Making it doesn't make you smart, it makes you stupid, right? That's what my point here. Arguments other than this can be made, and definitely that's fine. And I'm not expert there, but I do know this about statistical significance, and that's the thing that people don't understand very well. So, but let's move along. So, like I said, usually we don't know the variance, it's unknown. Instead, we have just samples, and we're assuming things are normally distributed. But we have the t distribution now. Remember that in the previous example, our statistics, the z here, it had the sigma because we thought we knew the variance. In this case, we don't know the variance. We know a sample variance, and the square root of that is the sample deviation. So the sample deviation here, in place of the actual known deviation, gives us a t distributed variable. And it depends on n, of course. The larger the n, the more closer this resembles the N01 distribution. And with smaller n, it's radically more flat distribution. So we get a test statistics here. We calculate it just as before. It's basically the same formula, except we're using the S instead of the sigma. But now we don't compare it to the N01 distribution, we're comparing it to the Tn-1 distribution. And nothing else changes here. So this is as test statistics as before. And here's an example. I'm not going to go here in great detail, but let's say the factory states that the diameter of a valve that they are making is normally distributed with an 8.04 millimeter average. A new batch is produced and 40 valves are examined. The average valve diameter in this sample is 8.038, and the sample deviation is 0.006 millimeters. So we're going to be rejecting these valves or accepting them, meaning we'll send them to the customers. And we accept a 5% chance of false rejection. So we want the 95% the confidence interval that they're not wrong. Well, not really. So we are going to be rejecting these if there is if this is a 5% chance. So you have to understand, this is not very good quality control, is it? We're willing to accept that they are fine unless they are very clearly wrong. Well, it's not too bad, but this, yeah, let's just go with this. So determine the p-value and discuss the effect on the risk level on the probability of having faulty parts. So here we can calculate the p-value, and just looking at this formula here. So if we calculate this t statistics now, we are going to be calculating t equal the average minus mu0 divided by s over the square root of n. So which in this case, our average is 8.038 minus 8.040, because that's our previous average, divided by the sample deviation, which is 0.006 over the square root of n, which is 40, so the square root of 40. So this would be my t statistics. In this case, I just calculated it, and I'm going to calculate it with the MATLAB. I'm not going to switch windows here. You can do it by yourself if you want. So we have 8.038 minus 8.040 divided by 0.006 divided by the square root of 40. As it turns out, I get a t statistics of minus 2.1082. That is my test value, the test t statistics here. And now I'm going to calculate the p-value of this, but for that I need the t distribution, and let me just go here. Let me just recall that. I have forgotten what the so it's TCD, yeah, TCDF, yeah, sorry. So I calculate the TCDF at minus 2.1082, and I need the N. In this case, the number was 40, but I'm going to put here, I'm going to recall that it has to be N minus 1 distributed. So my N is 40, yes, but I'm going to be using 39 there. So I'll put this in the, so this is what I input in MATLAB. I got this. This is my t statistics. And now I'm going to calculate the TCDF here. And now I got 0.02. So that means that the probability of getting a value of that is this small or smaller is about 2%. Now, if 5% chance of false rejection is acceptable, then we would have 2.5% at the left-hand region and 2.5% at the right-hand region. So we're going to be rejecting this because the chance of falsely rejecting here because of it's too small is 2%. So we have a 2.5% chance that we are willing to accept for two small parts and 2.5% chance for rejecting when they're two large parts. And this is 0.02, so we're going to reject these. Now, discuss the risk level, effect of risk level and the probability of faulty parts. So the p-value is 0.02. So what if we increase this chance of false rejection? What happens to the quality of the product? Anyone? Well, the thing here is that the probability of false rejection means that we reject parts that are perfectly fine. And that would be the type 1 error. The type 2 error would be that we accept parts that are wrong. So remember, when we have n equal here, let's say that we don't change the n. So if we increase our, decrease our chance of false rejection, the smaller this value is, then the larger the value is for falsely accepting, and vice versa. So we should actually make this percentage quite big, right? So you have to understand here that depends on how you're going to use the information from your test. You should either have small p-values or alpha values or large alpha values. In this case, a larger alpha value means that you're more readily rejecting, which means that you are you're protecting the customer in some sense. You're making it a smaller probability that you're producing faulty parts by having a larger alpha. But because, you know, the thing is, here's the null hypothesis, the nature of the null hypothesis, the problematic nature of the null hypothesis is evident here, because the null hypothesis is that everything is fine. And to reject the null hypothesis, something has to, when you reject the null hypothesis, you conclude that we're pretty sure that something is wrong. But the problem with this is that everything is fine as a null hypothesis leads to as a conservative estimate here. So the null hypothesis by nature is a conservative estimate. And if we want to be conservative in the sense that we're not shipping unless we're sure that they are fine, then we need to be less conservative about rejecting the null hypothesis, right? You understand what's going on here. So the type 2, type 1 errors. All right, move along. The last part of this today's lecture, testing the equality of expected values. I mean, think about it this way. We have two variables, let's say two populations, two samples from two different populations, and we wish to determine whether they are the same in terms of their expected values. If we take the null hypothesis and rearrange the terms a little bit. So if the null hypothesis is that the expected values are the same, then we can also say that the difference of the expected values is 0. And we have the sample variances, which are normally distributed, and assuming that the samples are well collected, independent. So let's say, I mean, for argument's sake, let's say we are talking about the average salaries of men and women, for instance, that they are not different, or the average, some average. We take as our null hypothesis is that there is no difference. We calculate the probabilities associated. So the averages, the difference of the averages should be normally distributed, because the average is normally distributed in both cases. And so the difference is a normally distributed variable with the expected value, which is the difference of the expected values, and the variance, which is the sum of variances of these averages. But the average, the variance of the average, or the sample mean, is the original variance divided by the sample size. So that's why we get this normal distribution. Now we can calculate the test statistics here. We just calculate this difference, right? If it's 0, if the null hypothesis is that this is 0, then this should be 0, 1 normally distributed like this. So this test statistics, and look, if we know the variances, then we can do this, and it's normally distributed, and that's fine. If the variances are unknown but equal, then we can combine the sample variances like this. The problem comes in here if we cannot assume either that we know the variances or that they are equal. If we try to use here S in place of S squared in place of the sigma squared, then we run into trouble, because then we cannot really say that this is, for instance, T distributed. That's the problem here. If the variances are, for instance, radically different, then this distribution is a very pathological distribution that we get. We cannot follow the t-distribution. If we know that they are the same, then we can just use the normalized sample variance and come up with test statistics there. The problem with this is that these are not usually assumptions that we can make. The best we can do, and we'll talk about that next lecture, is to first test whether it's reasonable to assume that the variances are the same. And if we come up with a test for the sameness of the variables, and we conclude that yes, we can assume that they are the same, then we can take the sample variances here, fix the sample variance by this formula. This is not any rocket science. If you look at the formula for the sample variance of this and the sample variance of that, then you can just combine those two as this is like the weighted average of those, weighted on the sample size. So the sample size times the sample variance plus the sample, well, not the sample size, but the divisor there, and divided by the common divisor there. We'll look at some examples or exercises for next week where this comes to play. I'll put that on exercises, but it's not that big a deal. Don't try to remember this formula here. Try to understand it better. We're running out of time, so I don't have time here, but we'll carry on from this. I'll look at this more closely next week. Here's an example of two things. We assume that they have the same variance, and we can calculate this. You can use MATLAB. I'll show that in the examples section then in the following week. Then we will move to testing the variances. And that's about it. The last part of that will be testing the variances, and then we're going to be done with this course. So there are not that many tests that we discuss here, but I want you guys to be able to understand these tests, the nature of these tests, how they work, and what they can and what they cannot reveal. Very important in the use of statistics, but also, I want you guys to be thinking critically in the case that if the underlying distributions are not normal, very far from normal, if they don't have reasonable expected values and variances, or if the sample size, and that's the worst, if the sample sizes are very small. I mean, there was this guy who said that, they have evidence that the 4G networks or something like this, I don't know, that's Wi-Fi networks cause cancer. And the evidence was based on this idea that I think they had 4 rats in cages. I mean, I think a total of 6 rats or 4 rats or something. Maybe it was 6 rats. 3 of the rats were in a cage near a Wi-Fi router, and 3 of the rats were put in tin foil across the room. And the cage was put in tin foil. And then the 2 out of the 3 rats near the Wi-Fi transmitter developed cancer, while only 1 of the 3, I could be talking about different numbers here, but the numbers were similar to this. 1 of the 3 rats in that tinfoil cage developed cancer, and they calculated all kinds of statistical tests and concluded that it's a statistically significant difference, and we should expect that the averages, the expected values are the same. Maybe it was 4 and 4, so maybe it was 3 and 1 or 3, something like this. But really, honestly, bullshit. So please be mindful when you read something. If the n is small, and by small we usually mean something like under 30, then unless we have strong reasons to believe that the actual variable is in fact very closely. Exactly, that is true. Lab rats are very prone to cancer. That's definitely what they are. That's why they use them in cancer research. They're very prone to cancer, and they're used in knockout studies where they knock out certain genes from the genome to see how it affects their cancer rates. They get cancer very easily, so because they get cancer very easily, then it's easy to produce to make sure that they get cancer, and then look at the effects of certain drugs or something like this. Not that it's necessarily a good model for humans, but at least from the from the biomechanical or the biochemical point of view, you can do all sorts of things with rat models. I don't condone unnecessary animal testing myself, but honestly, ridiculous statements can be made with small sample sizes. That's a good point, Alex. Thank you for pointing that out. Lab rats are prone to cancer, and that's why they're very popular in cancer research. Another animal very popular in animal model research is the fruit fly, because their generation gap is very small, and they breed very rapidly if they're just given food. So yeah, and the genome is widely and extensively mapped, and mutation rates and whatnots in studies. Yeah. All right, I think we're going to stop here. I'm going to do my best to make sure that for the holidays, which is now we have 1 week break here, that for the holidays, does that mean people working around you have no. The long-term mortality rate of people around me or you will be 100%. I'm just going to guess that with a p-value that is very, very small, none of us are going to live to be 300 years old. So the probability of that happening is very small. But for cancer, no, not necessarily. I think it's around 20. The prevalence of different cancers is about 25% in people, I think. I'm not sure if that's the correct number nowadays, but it's about roughly that. So there are 6 participants here, if I'm not wrong. Yeah, 6 participants in here. So you would expect about 1.5 of us to get cancer at some point. Sorry, dude, this is bleak, but that's the way it is. Yeah. Yeah. One of us is probably 2 of that's true. Yeah. Yeah, you logged in via 2 different things. Yeah. That's a good point. Yeah, so there are 5 participants, so 1.25 of us. Yeah, but one of us is probably going to, I mean, if I had to guess. I used to do this when we had I used to demonstrate this when I had a very large group of people come to the lecture. And I would say that I can guess the number of left-handed people in this group. I would calculate the number of people in the classroom, and then I would just calculate the 13% or what that percentage was. And I said that, plus or minus 2 for that. So I would, if there were 100 attendants, then it would be very rarely much off. Except when I started teaching the engineering students that were doing software engineering. And then the number of left-handed people dropped. I don't know why that is. So it seems like, it wasn't a very good, this was not the hypothesis that the population. Yeah. That's actually probably something that may contribute it, because I started teaching this international engineering students. Then I saw a radical drop in the number of left-handed and the proportion of left-handed people. So that's another test that I could make. I could make a statistical test saying that is the proportion of left-handed people, will it be smaller? And my guess is that it is. And then in many countries, this is true. I mean, people are taught to write with their right hand. If they're left-handed as children, then in many countries, people are expected to still write with their right hand. And then they have to learn to be right-handed. That's true. It happened in Finland also, like still, I don't know exactly when, but maybe 60 years ago they used to do that. I think in the 70s or something they stopped doing that. I still had a very old lady who was a teacher of mine in elementary school, and she would say that it's a tragedy that they are no longer allowed to force kids to write with their right hand, because it's so terrible watching people write with their left hand. Yeah. Yeah. I'm going to stop the recording now. We will